Let us talk about this problem. We are given an odd sized matrix and every row is sorted in increasing order and all the elements of this matrix are distinct. See, I have put these conditions to keep the question simple so that you can focus mainly on the logic. We can relax these conditions and still solve the problem using the same logic. Let's understand the problem with this example. We have 3 cross 3 matrix, total odd number of elements. What is median? See, when you have some elements and you want to find out their median, what you do is you consider those all elements in sorted order, you find the middle element. And if there are odd elements, then always there will be one middle element. And if there are even elements, then there will be two middle elements. And there can be multiple definitions of median. You can find the average of 2, you can return the first one or second one. The most common is average of 2. Here we are considering odd sized matrix. So we just have a middle element and we can return that middle element. So we have 9 elements, and if I write these 9 elements in sorted order, I'll have 1, 5, 10, 15, 20, 25, 30, 35, 40. And you can notice that every row is sorted in increasing order, right? There's no order among the columns, but rows are sorted in increasing order. If you consider this sorted sequence, you can notice that 20 is the middle element. That's why our output is 20. Now let's see this example. We have again an odd size matrix of size 3 cross 5, which means 15 elements. All the rows are sorted in increasing order. All the elements are distinct. If I write all the elements in sorted order, I again get this sequence. And if I take the middle element, I get the middle element as 8. So for this matrix, our output should be 8. Now please pause this video and try to think of a logic that takes a matrix and returns the median. Let us first talk about a naive solution to solve the problem. The idea is to consider the matrix elements and put them in an auxiliary array, right? So we simply traverse this matrix row by row and put all the elements in an array, right? Once we have put all the elements in an array, we sort the array. And after you sort the array, you can simply return the middle element. Now what is the time complexity of the solution? See, this step is going to take big O of RC time, if R is the number of rows and C is the number of columns. The second step is going to take big O of R into C log R into C, because we are sorting the 2D array. The third step is big O of one step. So this is the time complexity of individual step, and if you take the overall time complexity, it's going to be the highest order term, which is big O of RC log RC. That's the overall time complexity. We can optimize it. See, this second and third steps, they can be optimized. We can find median of an array in linear time also. There exists an algorithm, in fact a quick select algorithm, which we have discussed in the quick sort track. That algorithm takes big O of RC time on average. Although worst case it's big O of RC into log RC, but on average it takes big O of R into C time. So overall time complexity can be optimized to big O of RC. The solution that we just discussed does not use the fact that individual rows are sorted. Here we are going to discuss a solution which uses this fact and might work better than the previous solution. The time complexity of the solution that we are going to discuss is big O of R into log of max minus min multiplied by log of C. R is the number of rows, C is the number of columns. Max and min are maximum and minimum values respectively in the matrix. So please pause this video and try to think of a solution that works in this time. And to give you a hint about the solution, we are going to use binary search. Before we talk about this efficient solution, let's quickly compare the time complexities to understand why are we calling it efficient. See, the time complexity of the previous solution was big O of R into C. And the time complexity that we have here is big O of R into this log and log. See, log is definitely better. And how better it is? See, max and min, even if they have a difference of maximum integer value, which is 2 raised to the power 32, this log of base 2 and 2 raised to the power 32 is going to be only 32, right? It's only going to be 32. And C is also an integer value, number of columns, then also, this is also going to be 32 at most, right? If we consider 32-bit integers. So it's going to be 32 into 32, and here we have a value C. So if we have number of columns more than this range, right, this maximum value, and probably these ranges are smaller, then this solution is going to work better. And if you consider large inputs, large size matrix, then it is definitely better. Large size matrix and small ranges. Now please pause this video again and try to think of the solution. Here is the implementation of efficient approach, and this approach is going to use binary search. So in this approach, what are we doing? We are finding the minimum and maximum elements in the matrix first, and the minimum element will always be present in the first column and the maximum element will always be present in the last column. So what we do is we initialize the minimum element as the first element of first row and maximum element as last element of the first row, right? 0, C minus 1. After that, we run a loop from second row to onward, and in every iteration we compare the first element of current row with the min and last element of the current row with the max, and we update min and max accordingly. So after this loop, we have minimum and maximum elements in the matrix. One more thing that you would notice in the implementation is I have two additional parameters, R and C, right? In Java, you don't need to have two additional parameters, right? You can pass the matrix as a normal matrix and you can compute R as mat.length and C as mat0.length, right? You can compute that way. But to save the space on this whiteboard, I have taken R and C as extra parameters. So we compute the min and max in the matrix. In this matrix, the min is going to be 1 and the max is going to be 40. After we have computed min and max, we find the median position. Now what is median position? It's the count of elements smaller than or equal to the median element. For example, if you see this matrix, the median is 11. There are 7 elements smaller than this and 7 greater than this. And count of elements smaller than or equal to 11 is 8, right? If we include 7 and 11 also, right? 11, because we are considering equal, we get the count as 8. See, this definition is correct when we assume all the elements are distinct, and this whole implementation is based on this assumption that all the elements in the matrix are distinct. After we have computed the median position, we are going to do binary search in range from min to max, and in the binary search we are going to find the mid element, and then we are going to find the position of this mid element. How many elements are actually smaller than or equal to this mid element that we found? And then we are going to compare this mid position with the median position, and after comparison, accordingly we are going to decide whether we need to choose the left half or the right half. So you can notice here is we compute the mid element and then we find the position of this mid element. And how do we find the position of this mid element? We are using the property of our input question that every row is sorted, right? So we compute the mid element as 20. Right, and after I find the mid element as 20, we find the position by doing the binary search in every row, right? So we find the position of mid in every row and we add all the positions, right? We are adding all the positions that we found to mid position, and that's how we update the mid position. Now here we are using binary search really well, the binary search function of arrays class. See, the binary search function in Java, it returns you index of the element if it is present. And if it is not present, then it returns you the position where it should have been inserted plus 1 and whole minus. We'll understand this with an example. So 20, if you search here, you will get the index as 2. So count of elements is smaller than or equal to 20 is going to be 2 plus 1, 3, right? So that's why we have added 1. So we got the count as 3. Now if I search for 20 here is in this particular row, then binary search is going to consider the position where 20 would have been inserted. So 20 would have been inserted at position 0, 1, 2, 3, 4 and then 5, right? Because all the elements are smaller. Then the binary search function returns 1 to it, so it makes it 6 and returns you minus 6. Now what are we going to do? We are going to add 1 to minus 6, so we get minus 5, right? And since we may get a negative value, we are taking the absolute, right? So we'll get 3 here, then we'll get 5 here, and in this last row also we are going to get 5. So binary search will return minus 6, we'll add 1 to it, we'll get minus 5, and then we take the absolute value, so we get the 5, right? Now if I add all these 3 in the loop, I'll get the value as 13. Now this mid position, the position of the mid element is 13 and desired position is 8. We want the element which is at the 8th position. And here we got an element which is at 13th position. right? So we need to do binary search in the left half, and for that purpose we make max equal to mid. Now here you will notice one thing. In normal binary search, we update the index variables low and high, and we make low equal to mid plus 1 and high equal to mid minus 1. Instead of mid minus 1, we are doing mid here. See, the reason is, here we not only want to stop at an element which matches this position, we also want to ensure that the element is present in the matrix, right? So in equal case, we do not stop, and that's why we have this condition min is smaller than max, because in equal case we do not stop and we do not update max to mid minus 1, we update max to mid, right? So when you have a mid position equal to median position, then also you keep on running the loop, you keep on shifting max until min and max don't match, right? That's the idea we implement here. So we update max to 20, right? And after we update max to 20, we again compute the mid. We got the mid as 10, and now we find the position of 10. So we are going to get 2 here, then we are going to get 5 here, and then we are going to get 0 here. So we got 7, right? And now we see that we got the position as 7, desired position is 8, so we are going to update the min as mid plus 1. So we update the min as 11, and we run the next loop. We got the mid 15 and position as 10. This is greater. So we are going to update the max. Max is going to be updated to 15. We are going to compute the mid again, find the position by doing the binary search in every row, and we get the position as 9. Now this 9 is again greater, so we are going to update the max, and we are again going to find the mid equal to 12. Now you will notice that you found mid equal to 12 and its position matches with the desired position 8, but we do not stop our loop, right? We do not stop here because min and max are not same, and this is where this trick helps, right? And this condition also helps. Now what we do is we try to make min and max same. For that purpose, we again set the max as 12, right? We keep the max as mid, and then we compute the mid as min plus max by 2, which is 11, and we find the position of this as again 8, right? So next time when you see min and max, they become same, right? Because this 8 is equal to this position, and we again update the max as 11, and min and max, when they become same, we come out of the loop. So you can return either min or max, they both are same, so we return min here. Now let's quickly see the time complexity. This is clearly theta of r, and how many times this loop is going to run. We are doing a binary search from range min to max, so it's clearly going to be log of max minus min. And inside this loop, what are we doing? We are taking r time, theta r time, right? We are running a binary search for every row, and for every theta r, we are doing this binary search operation, which is going to take log c time. So log c into r into log of max minus min. That's the time complexity of this implementation.